Okay, so I left you thinking about what Hubble class our own Milky Way is from what you saw before the break. So most people think nowadays that the classification obviously is a barred spiral, so an S, capital S, capital B for a barred spiral, and somewhere between a little b and a little c in terms of the subclass. Again, it is a fairly subjective thing. So here's a couple of pictures of SBB or C ones from other galaxies, so that you can get a kind of a feel for what looking back at our galaxy might look like. You can see a bar in this one, a clear bar in this one. So this one perhaps is quite a good analogy to our own galaxy. You can see the two major arms coming off either end of the spiral there a little bit, I guess. Either end of the bar, that one and that one. That one looks fairly two-armed, whereas maybe this is more similar to the four gaseous arms that we have in our galaxy. Okay. So let's look a little bit more at how the disk of our galaxy rotates, and obviously just thinking of that as an example for other spiral galaxies as well. So here's an interesting fact. So by looking at the radial velocities of objects in all around us, we can piece together, obviously bearing in mind that the sun itself is rotating around the galaxy, so you have to take that into account when you only measure the relative radial velocity between us and whatever object we're looking at. But you can do that all the way around the disk of our galaxy and put together a model of what how our galaxy is actually rotating. And it turns out that for most of the galaxy, the disk, then there's a fairly constant rotation speed. So the speed at which stars and gas are rotating around the center of the galaxy is fairly constant, no matter how far from the center of the galaxy it is. Okay. So, and again, you don't need to remember this number, but the sort of speed is around just over 200 kilometers per second. Okay, it's the typical sort of rotation speed for our galaxy, and that, again, it's very similar, as we shall see later in the module, for other galaxies as well. Now, if you think about it for a moment, then the fact that the circular speed, if you like, or the rotation velocity is constant, means that the galaxy must be rotating differentially. Okay, so we've met differential rotation earlier in the module when we're talking about the differential rotation of the sun. Here we're now talking about differential rotation of the galaxy. And this means that stars closer to the center of the galaxy orbit in a shorter time than the ones further out. So obviously V is just 2 pi r over P. And so if V is constant, then it's telling you that P is proportional to R. Okay. So and here R is the radius from the center of the galaxy. So what that means is that stars closer into us than the sun have a shorter period. So they basically overtake us on the inside, if you like. And the sun has a shorter period than stars further out than the sun, and so we overtake the ones that are further out. So let's have a look at that. A couple of diagrams. So here is what we would call a rotation curve for the galaxy. So this is the orbital speed, so the speed at which objects are orbiting around the center of the galaxy from reasonably close in, inner edge of the disk, all the way out through to the outer edge at around 20 kiloparsecs. And ignoring the bumps and wiggles here, that's just details, but basically it's basically flat. If anything, it's rising. So that is what's normally referred to as a flat rotation curve, and it's very similar in all other spiral galaxies as well. And we'll come back to this in workshop 5, but I'll just highlight it here. So if you think about going back to Kepler's laws and how things orbit around a center of mass, like planets in the solar system, then the expected shape of a curve as you get far out to the outer parts of the galaxy would be something like this, that v is proportional to 1 over the square root of r, not just v as a constant, but r. If most of the mass is inside, then you'd expect the orbital speed to drop off. You can clearly see that it doesn't. And that has major implications for our understanding of how galaxies work, which we will come back to in workshop 5. So don't forget to attend that one. Okay, here's the idea of sort of stars overtaking each other and differential rotation. Okay, so here's the center of the galaxy. Here schematically is the sun going around in its circular orbit at 220 kilometers per second. And all the stars are going at 220 kilometers per second. But these ones further in are, they've got less of a circumference to do on their orbit. And so they will gradually overtake us on the inside. And similarly, we overtake the ones further out. So this is very much like if you've got a bunch of runners all going at the same speed on a running track, as they go around the bend, then the ones on the inside lane have the advantage, even if they're running at the same speed as the ones further out, and they overtake them. Okay. And so this is the whole idea of differential rotation. So there's a kind of a shear building up here, a shearing motion as you go further out. Okay. And that doesn't really affect the stars very much, but in terms of gas clouds and that kind of thing, it kind of gets them rotating and stirs them up. So again, it's another dynamical input of rotational energy, if you like, into the interstellar medium. Okay. So this idea of differential rotation, actually just let me make another point. So a good analogy to an alternative for differential rotation, of course, would be solid body rotation. Okay. And if you had solid body rotation, like a dinner plate, the period would be constant with r. And so that's the difference. Everything would, the stars on the outside would have to go around much faster in order to keep up the ones if the period was constant on the inside. Okay, so galaxies do not rotate in like a solid body at all. That's where the differential rotation comes in. So this leads us to something famously called the wind-up problem for spiral galaxies. And this will be much easier to explain with the diagram in a moment, but let me just put the words here first. So if the spiral arms were a fixed pattern in the stars and the gas, then the fact that we know galaxies rotate differentially would basically cause the spirals to wind up and get very, very tight in just a few revolutions of the galaxy. But all of the spiral galaxies that we see in the universe all seem to be, have a similar kind of spiral pattern. They're not wound up at all. So there's a conflict there. Okay. So, but the underlying assumption here was that if the spiral arms were a fixed pattern in the stars and the gas. So what we mean by that, like, if the sun happened to be in a spiral arm, that it would be always in that spiral arm, and the spiral arm would rotate at the same speed as the stars. So if you start with that picture, then you quickly get into this wind-up issue. So let's illustrate that with a schematic diagram, which is obviously starts off very idealized and not very sensible, but it illustrates the problem quite quickly. So let's consider 4 different stars here, A, B, C, and D, and they're all like B is twice as far from the center as A, and D is 4 times the distance from the center as A. And we're going to set them off, but with this differential rotation pattern, where the period of rotation is proportional to r, how far they are away from the galactic center. So you can see initially, they all start in a line, okay? Now let's look at the situation after star A has gone half an orbit. Star B is twice as far away, so therefore its period is only half of star A, because of the, is twice, the period of star B is twice that of star A. So yeah, it's only gone a quarter of an orbit. Okay. Let's keep going. So here's after A has been around once. So A has a much, half the period of B. So B has only gone half. And D, which is 4 times as far away as A, has only gone a quarter of its orbit. Okay. So you can start to see it's got a nice kind of spiral pattern now. Okay. But if we just go now and look at, let everything move on another orbit of A, so A's now gone round twice, D is still only gone around half an orbit, okay? And you can see that the line joining the 4 stars is already wound up much tighter than we actually see in typical spiral galaxies, and that's only, a couple of rotations of the innermost star here. So this is the kind of prediction that you would get if the spiral arms were a feature of the stars and galaxies, the stars and gas themselves. So what this is really telling us is that the spiral arm pattern does not rotate in the same way as the stars and the gas. So another way to say that is that stars move in and out of the spiral arms, and that the spiral pattern is literally that. It's a pattern that moves around at a different rate relative to the stars and the gas itself in the spiral galaxy. So obviously this is predicated on the fact that the galaxy has been around, rotated many times. Okay, so this is a little calculation you can do for yourself. Okay, so work out how long it takes the sun to orbit the galaxy, to go all the way around the galaxy once. Okay, so work out its period. Okay, so recall the sun is 8 kiloparsecs from the center and is moving at a speed of 220 kilometers per second. Okay, so you can work that out. How long does it take the sun to go around the galaxy once? And we know that the galaxy is 5 billion years old. Sorry, the sun is 5 billion years old. So how many times has the sun been around the galaxy in its lifetime? There's another supplementary there. Okay, let's have a go at that, and that will lead us into the next